Hey everybody, Meenal here, and welcome back to the channel. Today, we're diving into the fascinating world of logic gates, the fundamental building blocks of all things digital. You know how we always talk about computers thinking in ones and zeros? Well, logic gates are how they actually do it. These little guys are the decision makers of the digital world, processing those ones and zeros to make your computer, smartphone, and even your toaster do all the cool things they do. By the end of this video, you'll have a solid understanding of what logic gates are and how they work. We'll cover all the basic types, from AND gates to XOR gates and everything in between. So buckle up and let's get our logic on. Alright, so what exactly is a logic gate? Imagine a tiny electronic component that takes in one or more electrical signals, which we represent as ones and zeros, and spits out a single output signal based on a specific rule. That rule is what defines the type of logic gate it is. Think of it like a light switch. You flip the switch up, that's your input, and the light turns on, that's the output. Logic gates are kind of like that, except instead of just on or off, they can handle more complex logic operations. Now you might be wondering, why should I care about these things? Well, logic gates are everywhere in digital circuits. They're the brains behind everything from your CPU to your RAM to that fancy new graphics card you've been eyeing. They're what allow computers to perform calculations, make decisions, and basically do all the things that make them so awesome. And trust me, once you understand how logic gates work, you'll start to see them everywhere in the tech world. It's like a secret language that unlocks a whole new level of understanding about how electronics work. So, to break it down even further, each logic gate has a specific symbol that represents it, kind of like a shorthand notation for circuit diagrams. And each gate follows a specific truth table, which is basically a table that lists all the possible input combinations and their corresponding outputs. We'll dive into the specifics of each gate and their truth tables in the coming chapters. But for now, just remember, logic gates are the decision makers of the digital world, taking in those ones and zeros and spitting out a result based on a specific logical operation. They're the fundamental building blocks that make all the digital magic happen. First up, we've got the AND gate, and it's exactly what it sounds like. This gate only gives you a high output, a 1, if both of its inputs are high. It's like a strict bouncer at a club. You need the right shoes and the right ID to get past. The symbol for an AND gate looks like a sort of rounded off D. You've got your two inputs on the flat side and the output on the curved. Now let's look at the truth table. Remember, we're dealing with ones and zeros here. So if both inputs are 0, the output is 0. If one input is 1 and the other is 0, still a 0. Only when both inputs are 1 does the AND gate finally give us a 1 as the output. So where would you actually use this? Imagine a security system. You might have a door sensor and a motion sensor hooked up to an AND gate. Only when both the door opens, door sensor equals 1. And there's motion detected, motion sensor equals 1. Would the alarm trigger? Output equals 1. Pretty straightforward, right? The AND gate is all about making sure all the conditions are met before it gives you the green light. Next up is the OR gate, and it's a bit more lenient than the AND gate. This one gives you a high output, a 1, if at least one of its inputs is high. Think of it like ordering pizza toppings. You can get pepperoni or mushrooms, or even both. The OR gate symbol looks a bit like a spaceship, with a curved input side and a pointy output side. Now let's check out the truth table. If both inputs are 0, the output is 0. But here's where it gets interesting. If either input is a 1, the output immediately becomes a 1. And of course, if both inputs are 1, the output is still a 1. So where's the OR gate useful? Imagine you're designing an automatic watering system for your plants. You could have a moisture sensor and a timer hooked up to an OR gate. If the soil is dry, moisture sensor equals 1, or it's the scheduled watering time, timer equals 1, the system will turn on the sprinklers, output equals 1. The OR gate is all about flexibility, giving you a 1 if at least one of the conditions is met. Now, let's talk about the NOT gate, also known as the inverter. This one's a bit of a lone wolf, only taking in a single input. And its job is simple. Flip the input. If the input is 1, the output is 0, and vice versa. It's like that one friend who always disagrees with you, just for the sake of it. The NOT gate symbol is pretty easy to remember. It looks like a triangle with a little circle on the pointy end, representing the inversion. The truth table is also super simple. Input 0, output 1, input 1, output 0. It's literally just flipping the script. Now you might think, that's it? What's so useful about just flipping a signal? Well, you'd be surprised. The NOT gate is crucial for things like creating complementary signals, which are used all over the place in digital circuits. For example, in memory chips, data is often stored in pairs of inverters. If one inverter has a 1 stored, the other one will have a 0. This redundancy helps to ensure data integrity and prevent errors. So, even though it seems simple, the NOT gate plays a vital role in making digital systems work reliably. Now things start to get a little more interesting. The NAND gate is basically an AND gate with a rebellious streak. Remember how the AND gate only gave us a 1 if both inputs were 1? Well, the NAND gate does the exact opposite. It gives us a 0 when both inputs are 1. The symbol for a NAND gate is just like the AND gate, but with that little circle on the output end, indicating the inversion. Let's break down the truth table. If both inputs are 0, the output is 1. If one input is 0 and the other is 1, still a 1. It's only when inputs are 1 that the NAND gate says nope and gives us a 0. So what's this gate good for? Well, NAND gates are super versatile. In fact, you can build any other logic gate using just a combination of NAND gates. That's why they're often considered the universal gate of digital logic. Need to build an OR gate? No problem, just combine a few NANDs in the right way. It's like the Lego brick of the digital world. You guessed it, the NOR gate is basically an OR gate with that same rebellious streak. It takes the output of an OR gate and flips it, so it gives us a 0 if one of its inputs is a 1. The symbol for a NOR gate is just like the OR gate, but with that telltale inversion circle on the output. Time for another truth table breakdown. If both inputs are 0, the output is 1. But as soon as even input becomes a 1, the output goes to 0. Both inputs as 1, still a 0. Now just like the NAND gate, the NOR gate is also functionally complete. This means you can build any other logic gate using just NOR gates. So why use one over the other? Sometimes it just comes down to what's more efficient or cost-effective for a particular circuit design. Alright, we're in the home stretch now with our last two gates, XOR and XNOR. These guys are a bit more specialized. The XOR gate, short for exclusive OR, only gives us a 1 if of its inputs is a 1. Think of it like choosing between two desserts. You can have cake or ice cream, but not both. The symbol for an XOR gate is like the OR gate symbol, but with an extra curved line on the input side. Now let's look at the truth table. If both inputs are 0, the output is 0. If one input is 1 and the other is 0, we get a 1. But if both inputs are 1, the output goes back to 0. So, what's this useful for? XOR gates are great for things like error detection and parity checking in data transmission. And lastly, we have the XNOR gate, which, you guessed it, is just the XOR gate with an inverter on the output. It gives us a 1 if inputs are the same, either both 0 or both 1. Its symbol is the same as the XOR gate, but with, you guessed it, that little inversion circle. The truth table? Well, it's just the inverse of the XOR truth table. XNOR gates are used in things like comparators, which check if two values are equal. And there you have it. So, there you have it. A crash course on logic gates. These little guys might seem simple, but they're the fundamental building blocks of all the amazing technology we use every day. Hopefully, this video gave you a solid understanding of how these digital decision makers work and why they're so important. From AND gates to XNOR gates, we've covered them all. Thanks for watching. If you found this video helpful, don't forget to like, share, and subscribe for more tech content. And be sure to let me know in the comments what tech mysteries you'd like me to unravel next.